All right, so today we'll talk about hydrogen. What is this good for? It's a great energy storage device. Okay, so this is good for energy storage. Why do we say that? Uh, hydrogen, it's a dynamic molecule. Do you get free hydrogen on Earth? No, there's no free hydrogen on Earth. It comes in, it's here's a combined form it comes in. Okay.
I thought you meant price wise.
Oh, no. So, if we had free hydrogen, molecular hydrogen, then that would be great. This is, so this has a lot of energy in it. So, for instance, okay, there are two things we need the hydrogen for. And what I'm going to do is I'm going to summarize the chapter in these few slides here. Okay. For transportation, so what we currently do is gasoline, and we burn it. Okay. Gasoline, by the way, is H1618. Okay. We burn it. What does burning mean? Burning means combining it with oxygen. Okay. And I'm not going to balance the equation. And what you get is CO2 plus water plus energy. Okay. And and this energy in the form of heat, you convert, your car engine converts that to the motion of the car. Okay, so that's why we do this. Okay. What is the problem with this? CO2. So we've been talking about this all semester, and this is the problem. Okay. So now let's burn hydrogen. Okay, we're going to burn hydrogen. What does burning mean? Adding oxygen, combining it with oxygen. All right. In this equation, do you see anything? Any issues? No CO2? This would be great. And now let me tell you another kicker. Okay, so if you burn 1 kg of gasoline and you burn 1 kg of hydrogen, if you get X amount of energy, you get 3x amounts of energy. No CO2, 3 times the energy. Why the heck aren't we using hydrogen?
Because it's not free.
Hmm? So, so right now, all right, so here's why you don't use hydrogen in your cars, okay? So 1 liter of gasoline, 1 liter, hold your coffee cup up. That's 1 liter of gasoline. To get, so hydrogen is a gas, and you would need 2,500 liters of hydrogen at atmospheric pressure to get the same amount of energy. Okay, you can put that in your car. Now, to get the same amount of energy as gasoline from there, you would need 3 times this much hydrogen. That's the problem. Did you guys understand that? Okay. 3 times that much that's the volume inside your SUV. Okay. So volumetrically, this much gasoline, you need that much hydrogen. Okay. So this is gasoline. So essentially, you fill your tank with gasoline, you would need, at atmospheric pressure, you would need as much as, let's say, a semi's worth of hydrogen to get the same amount of energy. Okay, that's the problem. So is there anything you could do for that? Anything you could fix it?
Compress it.
Compress it, very good. So compress this, okay? And that's what is shown here, okay? So in this diagram, so here's compressed hydrogen, yep. And we'll see how you can use compressed hydrogen in a fuel cell, okay? What a fuel cell does is it takes hydrogen and converts that into electricity, okay? And we'll come to that, okay? And so you can use that in transportation. And once you produce electricity, you can have an electric motor like Tesla and run the car, yeah? And what comes out of your tailpipe? I'm
Water
sorry?
vapor.
Water vapor, okay? Water vapor and no carbon dioxide. So this would be great. All right. So that's transportation. We'll come to that. Another way, what you can do is instead of compressing it, you can also, here's another way to do this. What you can do is take a metal, these blue atoms are metal, and put hydrogen in the spaces between the metal. So you can pack a lot of hydrogen in a small space. Okay? So this could be your gas tank in your car. Yeah. What is the problem with this?
Difficult to get it
I'm sorry?
out quickly.
Yeah, so you read that. What's the other problem with it?
It's heavy.
It's heavy. All right. So you guys read that. All right. So anyway, hydrogen has a lot of energy content. Okay. It's just to make it more practical. Okay. The Japanese, by the way, are betting on hydrogen. Okay. Now here's another thing we want to do. So transportation, energy storage. Now we'll talk about energy storage. Yeah. All right, so you burn hydrogen and you get energy. All right, now you can do the reaction in reverse. You can take water and add energy and you get this. So what happened here? Okay, so this was the input. You put in energy, and where did the energy go? I'm sorry?
To create the bonds, the energy is in the bond.
Yeah, it got stored here. That's what happened. Okay. So this is the energy storage mechanism. Okay. Well, how do you put in energy? There's three ways we can. We'll talk about this. Three ways. So this is producing hydrogen to store energy. Okay. So how can we supply? We can supply electricity. Yeah. How do we get the electricity? From solar panels and wind energy. Okay, so this would be green energy. This would be green hydrogen. Okay. You could use heat. You could provide heat and chemical processes. Okay, so you can provide energy using heat. So if you have heat in a coal power plant, excess heat that you're throwing away, you can use that to produce hydrogen. From a nuclear power plant, you can supply heat to produce hydrogen. Okay, and so once you produce hydrogen, you can use this hydrogen to produce electricity later. Okay, so here that's a mechanism for storing energy. Do you guys remember what is the largest technology for storing electricity currently? How's energy stored the most right now? Very good. That's water. So you have two tanks. one tank at a lower level, and okay. So when you have excess electricity, you pump water up, and when you need the electricity back later, you dump the water and produce electricity. Okay. So this is currently the biggest battery you have. Okay. So now that you've learned that you can use water, take excess electricity, and produce hydrogen, you've stored energy there. And then you can use the hydrogen to produce electricity back. Okay? So hydrogen is a great mechanism for storing energy. Okay? So here's a future zero carbon footprint scenario. Yeah, so okay, so you produce electricity using wind and solar. Okay? You use this energy, put it in water, and produce hydrogen. So you've stored this energy in hydrogen. And you can store the hydrogen. How long can you store the hydrogen? As long as you want. Yep, forever. Okay? And then you can use this hydrogen in a fuel cell. We'll see how the fuel cell works later in the chapter, and produce the electricity whenever you need it. Okay? So here's a net zero scenario. Okay. Why aren't we doing this right now? Right now, this electrolyzer is a little expensive. Okay, but we're getting there. Okay, it's almost getting to be cheap enough. Okay. All right. So hydrogen is a great way to store energy. Okay. So I'm sure within a couple of lifetimes, this will. Within 10-15 years, this should be economically feasible. Okay. All right. So do you guys understand this? Okay. So now we'll get into the details. Okay. So again, for transportation, what you need is you need to be able to compress the hydrogen or pack it in metals so that you can use the hydrogen in fuel cells and use the energy for transportation. Okay. All right. So let's get into this. So we'll talk about these various things. Okay. Hydrogen is a mechanism for storing energy. Okay. So look at this. Energy per kg. 1 kg is 2.2 pounds. Okay. So energy content, this is in megajoules per kg. Gasoline has about 50 units megajoules per kg. And look at hydrogen. Hydrogen has 3 times as much, 150 megajoules per kg. It's just that, like we said, the volume is that much gasoline. Her cup full of gasoline is equivalent to 3 times that. Okay. To get the same energy as one glass full of gasoline, you have to fill an SUV, the insides of an SUV with hydrogen to get the same energy. Okay?
How do you compress it?
Well, the air in your tires is compressed. The air in your tire has this 4 times the pressure, or 3 times the pressure that's in this room. A compressor is just a fan which is pushing air into a smaller and smaller area. Okay, well, it's pushing more and more air into a given volume. And that's how you're compressing it. So except that, so the pressure in your tires is 3 atmospheres. To make it feasible, you have to compress hydrogen to about 70 atmospheres. Okay, so you have to compress it quite a bit. All right, so again, you can burn hydrogen to get energy. So you get energy here. And as we said, you get 3 times the energy of burning from burning gasoline. Pound for pound, you get 3 times the energy. Okay. So, as can be, okay, so here again, here are the numbers. Gasoline, megajoules per kg. This is just numbers of that graph. Okay, so for gasoline, you get 44 megajoules per kg, and for hydrogen, you get 142 megajoules. Okay. So, pound for pound, you get a lot more energy, but if you look at it volumetrically, what this is saying is that much. 1 meter cube is that computer Carol. That's 1 meter cube. Okay, this much hydrogen. This much hydrogen has only 12 megajoules of energy, and that much gasoline has 35,000 megajoules of energy. Okay. So what you want is high density. The thing about gasoline is it packs a lot of energy and it's in a small volume. What is the bad thing about it? CO2. Yeah. All right. So again, that's the problem we're trying to solve. Okay. Again, so here's a hopefully very near future scenario. You produce green electricity. You electrolyze water and store that excess energy in hydrogen, and you store it as long as you want. And then you use the hydrogen in a fuel cell to produce electricity whenever you need it. Yep.
How do they separate out the hydrogen from the oxygen? During after the electrolysis?
Oh, well, we'll come to that, but anyways, so, okay, let's do it right now. So here's an electrolyzer. The hydrogen is coming out at the cathode and the oxygen is coming out at the anode. Okay, they're coming at 2 separate places. All right, so here's the deal. So here are the numbers on this. In principle, about 64% of the energy can be recovered. So what this means is 80% efficiency of electrolysis and 80% of efficiency of fuel cells. Let's understand these numbers. Okay, so if you put in 100 units of 100 joules of electricity, what you have stored is 80 joules of energy in hydrogen. That's what this 80% efficiency means. Okay? And now if you take 100 joules of energy stored in the hydrogen, what you're getting is 80 joules of electricity out. Okay? Those are the best case scenarios. Okay? So, in net, the net efficiency is 0.8 times 0.8, which is 64%. So what we're saying is if you took 100 joules of electricity to start off with, you get 64 joules of electricity out in this process. All right. I put $100 in the bank, and I am getting out $64 from the bank. Why the heck would I do that? Yeah.
Because it's more efficient than other ways of storing energy?
Better for the environment.
This is free bucks. This is free. I don't care. I'm picking this off the street. Okay, so this is a great way to store energy. Okay, right now you're doing this. I mean, you get in your car, for $100, you're getting $20 worth of motion. You're doing it all day long. Right? Yeah. And you're paying money for the $100. This is free. Yeah. All right, so anyway, those are the numbers. Do you guys understand that? And again, this is the best case scenario. Yeah. All right, make sure you understand this stuff. Yeah. Yeah. All right, so hydrogen is a way to store energy. So now we'll look at how to produce hydrogen. Okay? So what we're going to talk about is this equation. Okay. We're going to take water and we're going to add energy and produce hydrogen. Again, this is not a balanced equation. So this is where you have stored energy. Okay. All right, you can provide energy one of three ways, and that's what we're going to talk about. Electrolysis, you're providing energy using electricity. Where is the electricity going to come from? Solar and wind. Okay. Or you can use heat. What you're doing is you use heat and you're just splitting the water molecule. Okay. Or you can use energy derived from a chemical reaction. Okay. So those are the three ways of doing it. Okay. And in practice, eventually, this is getting cheap enough. Okay. Right now, it's a little expensive, but once this gets to be cheap enough, we'll all be good. Okay. All right. So electrolysis, we'll talk about this first way of providing energy to produce hydrogen. Okay. All right. Okay. So electrolysis, there are two main electrolytic technologies, alkaline and proton exchange membrane. The alkaline electrolysis is 70% efficient, and the proton exchange membrane is about 80% efficient. And this is more expensive, but it's more efficient. Yeah, but hopefully the prices will become cheap. Okay. So here is where the 80% number comes in. So industrial production of 1 kg of hydrogen. So we have this process down. I mean, we can do it in large scale, which has a specific energy of 143 megajoules per kg, requires 180 to 200 megajoules of electricity. So what this number is saying is, I'll say, you need 186 megajoules of electricity to produce 143 megajoules of hydrogen. What you're doing is you're producing 1 kg of hydrogen. Okay. So, and 143 divided by 83. So you spent this much money and you stored this much energy is what that number means. Did you guys understand that? And I'm going to calculate that. Oops. So this is 80%. Okay. All right. So again, you take water, provide energy with electricity, and you produce hydrogen. Okay. Electrolysis, I'll come to the details in a second. Electrolysis is the best known and most efficient method of producing hydrogen. Okay. It is a separation. Okay. Hydrogen is formed by decomposition of water at the cathode. Okay. So let me get to that. Okay. What is water? Well, water is H2O. But in water, a small fraction, about 1 in 10 million, they ionize. Okay, OH. Every 1 in every 10 million roughly ionizes like that molecule. Yeah. So what you do is, so here's hydrogen, and here's a hydrogen ion, and here's a hydroxyl ion. This is a battery which is providing electricity. Electrons flow from here and go there. And this hydrogen will grab the electron and become a hydrogen molecule. Okay? And so this electron grabs and it becomes hydrogen, and so hydrogen is bubbling out. And the hydroxyl molecule is repelled by this negative electrode and goes toward there. And goes toward there, and it loses its electron, which goes through flows out of here and comes back to the battery. The electron started here, got absorbed by the hydrogen, the hydroxyl ion moved over here, it gives up its electron, which goes out here and comes back to the battery. Okay. And hydrogen is produced here, the hydroxyl ion moved over here, and the hydroxyl ion, when it comes there, it gives up its electron, and it produces, oxygen is produced there, and water. Okay? So oxygen bubbles out of here, hydrogen bubbles out of here, and to separate it, all you do is have a separation chamber where the gases don't mix. Okay? So you took water, you provided energy through electricity, and what you got is hydrogen, a stored molecule. Okay? So here's another way to look at it. Okay, so from an energy perspective, here's water is in lower energy state, hydrogen is in a higher energy state. You provide energy and you went from here to there. Okay, that's what you did. Okay. And then whenever you want to use this energy, you can burn or produce electricity that using that and get the energy back. Okay. And that's the idea. Okay, to enhance the process, the electrical conductivity of water is increased by dissolving an ionic compound such as sulfuric acid or potassium hydroxide. So you can mix sulfuric acid or potassium hydroxide to enhance the reaction, okay, to have more of these ions. Okay, so hydrogen can be used to store store electricity when it's not needed, and then used to meet power needs when needed, or to fuel vehicles. The storable quality of hydrogen helps make hydrogen an enabler of wider use of renewables. Okay, so again, what is it that's stopping us from using solar and wind right now? Because yeah, you don't have a cheap enough storage mechanism. Right now, solar and wind are the cheapest sources of electricity. Yep. It's just that they're very intermittent, and you have to come up with this cheap enough storage technology. Okay? And it'll happen within your lifetimes. Yep. So the future looks good for you guys. Yep.
Does the salt or acid make it so that the electrolyzer can only do it a certain amount of times, or can it do it pretty much indefinitely?
Say that again.
Does the sulfuric acid
Mm-hmm.
give the electrolyzer a shelf life, or can it do it infinite?
Yeah, it's infinite.
Okay.
Yeah. You keep adding water
Okay.
as you're producing more and more. Okay. What you're doing is you're converting water into hydrogen. Okay. So as you're running out of water, you keep adding. Okay. So what does this say? Okay, what does it mean?
The temperature of the makeup of water,
What's that?
the temperature of the makeup of water.
Okay, so what we are interested in is we are producing hydrogen, and we're going to take water and we're going to provide energy to produce hydrogen. And now we just learned about how to, when you provide energy via electricity, that was electrolysis. Now we're going to provide heat. Just heat the heck out of it, that's all. Okay. Where's the heat going to come from? Well, in nuclear power plants, there's excess heat and stuff like that. Wherever the excess heat, there's excess heat, we're going to use heat to split water. So for instance, I believe at 2,500 degrees Celsius, water would just split, okay? and produce hydrogen. But that's not an efficient way of doing it. So we will figure out how to do this. So thermal decomposition of water. Okay, decomposition of water can be accomplished using thermal rather than electrical energy. A catalyst facilitates the process. Okay, so in this, iodine acts as a catalyst. Okay, so thermal decomposition reactions begin by heating sulfuric acid. So here's sulfuric acid, and so you're providing heat. So anything on the left-hand side is input. This is input. Okay, so you take heat, sulfuric acid splits into that, and then you're providing further heat, and the sulfur dioxide plus iodine plus water splits, becomes hydrogen iodide and sulfuric acid back, so you don't lose your starting material. What is your end goal? Your end goal is to split water into hydrogen. Okay, so any other ingredients that are used, those are catalysts, and you need them back. Okay, and then heating hydrogen iodide splits into hydrogen. Okay, so you're providing all this heat. You started off with this, and this was also an ingredient. You're getting that back, you're getting that back, and hydrogen. So all that heat got stored into this hydrogen. Yep.
Do you need those to help split it up, or is that just like?
Yeah, I mean, so you eat a burger, and if you didn't have your digestive enzymes, you'd never digest the burger. And what are enzymes? Enzymes are catalysts. They make reactions go faster.
Could we use like the water that we, like the, okay, hopefully I'm like thinking about this the right way,
Mhm.
but like a couple chapters back, you know, we're learning about the nuclear, and then we put the heat into the water,
Mhm.
and that would technically split the hydrogen and the oxygen, so couldn't we use that for?
Yes, so, okay. So in a nuclear reactor, here was the reactor, nuclei were splitting and you were producing heat. Okay? Then what you had to do was you had to take this heat, transport it someplace, and this was a turbine where the steam was spinning this turbine. What was the goal? And then you went to a generator. Okay? Remember, your goal was to turn that piece of wire in between magnets. Okay, so that's what the whole thing was. So the heat had to be transported, and you boil water, turn it into steam, which turns the turbine, which turns that wire in between the magnet. Okay. So that was the goal there. But there is excess heat because remember, how much of this heat gets converted to electricity in a nuclear reactor?
Like 60% or something?
35%. Okay? So the other 65% has to be thrown away. Okay? And you can use that excess heat to produce hydrogen. Okay? I mean, some of that heat to produce hydrogen. You can't use all of it. Okay? All right, so here's another way to get heat. You focus sunlight and heat some. So here's a solar thermochemical reactor, and you can produce hydrogen. Okay. All right, so you took all this heat and you produced hydrogen. Okay.
I have a question.
Mm-hmm.
So, with the hydrogen iodide, you're using
Mhm.
with the leftover, you have hydrogen and iodine,
Mm-hmm.
right?
Mm-hmm.
So you're using the hydrogen to store
Energy.
energy,
Mm-hmm.
but then you have the leftover iodine.
Well, all this is in the mixture
Right.
that never gets used up. It's facilitating the reaction.
Right, so
Mhm.
wouldn't you just, like, I don't wanna say it's left over,
Mhm.
but since it's not being used,
Mhm.
it's just there,
Mm-hmm.
and you keep doing the reaction, I guess you could say.
Well, what has happened is you're using up water,
Mm-hmm.
so you have to keep filling it with water.
So it just dilutes it?
Well, I mean, once the water gets split, it makes it more concentrated, so you have to keep adding water.
Okay.
Yeah. Yeah. So what is happening is ultimately what happened is, yeah, so there was all these intermediate steps, but this was the essence. You took water, you provided heat, and produced hydrogen and oxygen. Hydrogen was removed, oxygen was removed, and your water is going down. So you gotta keep adding water. Yeah. All these guys were just sweet talking the water into splitting. That's what was happening. That was the job of the catalyst. Okay. All right, so it turns out that, okay. So what we have learned is okay, so this is what we're going to talk about now. You can take water, put in electricity, and split it into hydrogen and oxygen. This is electrolysis. Okay. And you've stored this energy in here. Okay, what we're going to do is we're going to talk about high temperature electrolysis. If this water is hot or if this is steam, then you need less electricity to produce hydrogen. Okay. All right, so that's what this is showing you. See, the temperature of the steam to produce hydrogen. So as the steam temperature is higher, the amount of electricity needed is less and less. Yeah. But you are ending up providing more of the energy through heat. So here the total energy input is higher, but this heat you were going to throw away anyway. So if you had some place where you had heat that was being wasted, you use that heat and you'd have to produce less electricity to produce hydrogen. Okay. Where's this electricity coming from? Wind and solar. Okay. So with less electricity, you're producing more hydrogen. Okay. Yeah. So that's the idea. Okay. Okay. So when energy supplied is in the form of heat, the best path to production of hydrogen is through high temperature electrolysis. So again, we're trying to produce hydrogen as the best possible way. Okay, so research into high temperature nuclear reactors may eventually lead to a hydrogen supply that is cost competitive with natural gas steam reforming. Okay, right now, hydrogen is being produced with natural gas and hot steam. Natural gas is CH4. Okay, so and you can produce hydrogen using methane. Okay, and heat, but and water, I guess. And it still gives you carbon dioxide, okay, but and stuff like that. So, but still the carbon footprint is smaller. But if you produce hydrogen from water, then you have zero carbon footprint. Okay, right now this is the way to produce. So that's what this is, with natural gas steam reforming. Okay, but we want to produce hydrogen using water, and so high temperature nuclear reactors will lead to hydrogen supply that is cost competitive and green hydrogen. Okay, so this is not green hydrogen. Yeah. So, but this is not available at a commercial scale yet. So here's natural gas reforming, here's methane, natural gas, steam, and what you produce is carbon monoxide, and hydrogen, and then this carbon monoxide is carbon monoxide, and steam reacts in the presence of a catalyst to produce carbon dioxide. So this you convert to carbon dioxide using steam. Yeah. So you are producing hydrogen, but you're also producing carbon dioxide, which you don't want. Okay. But producing hydrogen from electricity and water, there's no carbon dioxide produced. Yeah. So natural gas reforming is an advanced and mature production process. Today, 95% of the hydrogen produced in the US is made by natural gas reforming in large plants. Okay. High temperature steam is used. Okay. And methane reacts with steam under 3 to 25 bar pressure. So that's 1 bar is 1 atmosphere essentially. Okay. Okay, so now we'll talk about storing hydrogen. So we've talked about production of hydrogen. Okay, so hopefully soon all of the hydrogen will be produced by this method, electrolysis. This is clean. Again, 2H2O. This is clean, and right now it's not being used just because it's a little expensive. Okay, so you've produced all this hydrogen, and now you've gone to store it. Okay. The thing is, why do you? So, if you produce a lot of hydrogen, okay, the volume is at atmospheric pressure. It'll be one car gas tank full of gasoline is equivalent to 1 semi worth of hydrogen. Okay, I mean that's too much. So what you do is you have to compress this. So you can compress hydrogen. You can store it by turning it into a liquid, or you can store it in metals. Okay, so those are the 3 ways we're going to talk about. Okay. So you want this if you want to use it in transportation and stuff. Okay. So this shows you the hydrogen. Okay. So you've stored a certain amount of hydrogen at 200 atmospheres. Okay. And this is not practical for cars yet. Okay. So, and that would be the volume of hydrogen you would need for the car. This is if you had it in liquid form, and this is if you had it in metal hydride form. Okay, metal hydride being hydrogen stored in between metal like that. Okay, so that gives you a sense for the magnitude of the problem. Okay. So now we want to figure out hydrogen storage. Okay, you produced hydrogen and you're trying to store hydrogen. Okay, so this gives you the numbers. This is compressed hydrogen gas. This is compressed at 350. This is 35 megapascals. 1 megapascal is 10 atmospheres. Okay. So this is 350 atmospheres. Energy per kg is, again, 2.8 megajoules per kg. And again, you're always comparing to gasoline because gasoline is what you're trying to replace. Okay. Okay. Gasoline is very convenient. We have the infrastructure. You just pump it. It has high density and all that stuff. Okay. This is clean fuel, but it's it has a large volume. That's the problem. Okay. Even the energy content is 3 times, so 3 times 3 is 9. You're still behind. Yep. So this is compressed gas. This is liquid hydrogen. This is hydrogen in a metal. Okay. Now, when you compress hydrogen, you're wasting some of the energy. So the energy needed is, in the case of compressed hydrogen gas, the energy needed is that. Okay, a factor to consider for storing hydrogen is efficiency of the process. How much energy is needed to store the hydrogen? Okay, so you're wasting some of the energy to store the hydrogen. But you're doing that for gasoline as well. Gasoline is produced in factories, in refineries, in various places. And to transport gasoline to the pumping station, you have to transport it. You're spending some of the gasoline for that. Mm-hmm.
So
Mm-hmm.
with using compressed hydrogen gas,
Mm-hmm.
wouldn't you still be getting like basically more miles out of it since it's more efficient?
Yeah, yeah. I mean, this is the way to go. It's just that.
Even if it's like a small amount, wouldn't you still be getting the same, like, not the same amount of miles, but like if you fill your tank with that? it was-
Yeah, well, the problem, I mean, right now, if you can't compress it, okay, so let's say you going to keep your car size, whatever it is, and we are going to use your entire trunk space to have compressed gas, hydrogen gas. Okay, you might get a range of 150 miles. You have to refuel more often,
Right,
but no tailpipe emissions.
yeah.
So if you're willing to do that, and then refilling gas, hydrogen takes a little longer. I mean, not that much longer, but anyway, you can do all of that. The thing is, to replace gasoline, you just have to make it, you have to provide the same range and comparable refueling times. Okay. Even Tesla with half an hour of charging, it's still a thing. Okay. All right, so what this graph is showing you is as you compress hydrogen, these are 1,000 atmospheres. Okay. The volumetric density, okay, decreases. This is liquid hydrogen. Okay. What you want is density, high density, meaning you want a lot of hydrogen for a given volume. Okay. So this shows you, okay, so this is the ideal gas law, PV equal to nRT, and density is mass per unit volume. So from this equation, volume is nRT divided by P. And volume is nRT divided by P. Okay. And so we take 1 mole, and so MP over RT. Okay. So the density is, okay, mass divided by that. Anyway, okay. So so at higher pressure, you see hydrogen doesn't behave like an ideal gas. Now, liquid hydrogen, so to make hydrogen liquid, you have to cool it to 20.3 degree Kelvin. That's very cold, okay? And so you're spending energy doing that, okay? What you're trying to do is, okay, so you produced hydrogen. So this is your earnings. This is the energy you've stored. Now to store this, if you have to spend money, what you're trying to do is spend as little money as possible. Okay? And if you store it as liquid form, well, if you store it as liquid form, you're storing it in very small volume that is convenient, but it costs you money. That's the deal. Okay? So the density of liquid hydrogen is greater than the density of compressed hydrogen gas. So you need less volume to store that. And then presumably you can transport it as well if needed. Okay. Now, when you store liquid hydrogen, okay, so here's another deal you have to consider, okay. So here the hydrogen, what is the hydrogen? It has a proton and an electron. That's a hydrogen atom, okay. A hydrogen molecule has, so this is a hydrogen molecule. And what this says is, see, the proton has a spin, so the proton is spinning, okay, spinning like a top. And if it's spinning like this, here's the spin direction, okay. So if both of them have spin like this has more energy, okay. This has more energy than this guy, all right. So if you turn it into liquid and 75% at room temperature, 75% of the hydrogen is like this, 25% of the hydrogen is like this. And you convert it into liquid, and eventually this guy will go and become like that and release heat and turn some of this liquid into gas. So some of your money got thrown out, and that's all, okay. So you have to worry about stuff like this, okay. And that's what this is saying, okay. So at room temperature, thermal energy causes a mixture of about 25% parahydrogen and 75% orthohydrogen. So this is parahydrogen, this is orthohydrogen, this is higher energy than that. So if you cool it fast, then this you get 75% orthohydrogen, which will release heat, and some of your liquid will turn into gas, okay. All right, here's another way to store hydrogen in the gaps between metals. So this is metal hydrides, okay. So again, two problems with this is you got to come up with a technology where you can get in the hydrogen in and out fast, and if you could use a light metal, that would be good, okay. All right, now I want to make sure you understand fuel cells. Okay, so we're running out of time, but so what do fuel cells do? They will use hydrogen as fuel, and what you're getting out is hydrogen as fuel, and you will need air, oxygen to combine with the hydrogen, and what you're getting out is and then you're getting electricity, okay. So you're using hydrogen and oxygen, you're getting electricity, and you're going to run your car or whatever it is you're going to do with this electricity. And what you're getting out is water, is your exhaust, no carbon dioxide, okay. Okay, so fuel cells transform the chemical energy in hydrogen to electricity. Fuel cells need a continuous supply of fuel and oxygen, so they need a continuous supply of hydrogen and oxygen. Apparently, forklifts, people use in forklifts and stuff like that, they use hydrogen. Okay, I don't know if anybody's worked in a big storage place. Okay. So fuel cells produce relatively few pollutants compared to conventional combustion-based power generation. Okay. Okay. So fuel cells were invented in 1838. Yeah. And right now there's $1 billion worth of market for fuel cells. That's not much, but they're used to power fuel cell vehicles, including forklifts, automobiles, buses, boats, motorcycles, and submarines. Okay, so fuel cells are used. Okay, so here are the various kinds of fuel cells. Okay, these are the catalysts that are used. Okay, and their efficiencies are given by this. So the solid polymer fuel cells is the most efficient, 80% efficient. What does that mean? That 80% efficiency means the energy content of H2, 80% of that is converted to electricity. Okay, that's what that means. So there are many types of fuel cells. but they all consist of an anode and a cathode and an electrolyte that allows positively charged hydrogen ions to move between the two sides of the fuel cells. The anode contains a catalyst that causes oxidation of the hydrogen, okay, generating hydrogen ions and electrons. The hydrogen ions are then drawn through the electrolyte toward the cathode after the reaction. So the catalyst would, okay, so now we'll go to that. Okay. So, okay. Okay. Hydrogen is ionized at the anode by the reaction. Okay, so you put in hydrogen here, and at the anode, using a catalyst, the hydrogen is stripped off its electrons, and these electrons go through the external circuit. And the positive hydrogen ion go over here. The electrons come over here. The oxygen combines with the electrons, and it becomes negative. So, and the negative oxygen combines with the positive hydrogen that's coming here, and these two neutralize each other and become water. Okay. So again, what is happening is the hydrogen is giving up the electron easily, and the oxygen wants the electron bad. Okay, so that's, okay, it's like this. Okay, let's say she doesn't like donuts too much. Okay. So all you have to do is give her $1 and she'll give up her donuts. Okay, so, and I like donuts a lot. And then you sell me the donuts and I'll give you $5 for it. So you came out ahead $4. That's the idea. Did you guys understand that? And that's what the fuel cell is doing. Okay, so the hydrogen is giving up its electron easily, and the oxygen wants the electron bad. Okay, so there's the energy that you're getting. Yep. All right, so that's what the fuel cell does. Okay. So what you do is first separate the electrons from the hydrogen using a catalyst at the anode. This hydrogen, this travels through the external circuit. The 2x excess electron travel through the external circuit. So at the anode, the catalyst helps this process. The electrons travel through the external circuit, doing whatever it is that they do, and travel through the external circuit to react with the oxygen at the cathode. So the oxygen takes the electrons, and water is formed there. The hydrogen ion travels there and interacts with the oxygen, okay, and produces water. So you got electricity, and you're using catalyst, and water is the output, exhaust. Okay. I urge you guys to go see this YouTube video on the fuel cells. Okay. So again, what are we doing? We are using this is what the fuel cell is doing. Okay. It's converting the energy content of the hydrogen to electricity. Okay. All right, so here would be a future car. You would you can already buy fuel cell cars. Kennedy Space Center has hydrogen filling stations. There aren't many hydrogen filling stations, but anyway. So you would use a hydrogen tank. This would be the fuel cell. The fuel cell converts the energy content of the hydrogen into electricity. And you can charge the battery and run an electric motor, okay? Or you can use the electricity directly to run the electric motor. Okay. Again, this is a 2020 diagram. None of these states have hydrogen filling stations. California has some. Yeah. And these guys have a few more. To adopt a new technology, setting up the infrastructure takes a while. Okay, just like the charging stations takes big bucks and takes a while to set this up again. All right, guys. So, what did we learn today?
How to store hydrogen.
How to produce hydrogen, and it's a great energy storing device. So you take water and energy, and you store that energy in hydrogen. Yep. All right, guys. So I